Dear students, Assalamu alaikum.
Walaikum assalam.
Walaikum salam, sir.
Dear students, Assalamu alaikum. Today we are going to start online lecture of quantum mechanics, third lecture. This lecture is all about the operators, quantum mechanical operators. First of all, we will discuss the definition of quantum mechanical operators, its mathematical perspectives, and then I will discuss some of the properties, mathematical properties of the quantum mechanical operators. And then we will discuss a few types of the quantum mechanical operators. And at the end of the lecture, I will discuss the physical significance of these operators, what are the usage and advantages in quantum mechanics, and the comparison with classical mechanics. So, okay, now let's start. I'm going to share the screen with you so that we may start it properly. Okay, operators. What are the operators? What are their mathematical definition? You know, in classical mechanics, you have dynamical variables like momentum, like angular momentum, like kinetic energy. So they define different properties of a moving object. But how one can define these properties in quantum mechanics? There is not a direct way to calculate any dynamical property in quantum mechanics because the particles are invisible in nature and we cannot directly predict and measure the properties. So we have to comply on some mathematical ideas, some mathematical formalism. So for each dynamical variable in classical mechanics, there corresponds a quantum mechanical operator. Like in classical mechanics, we have a position, like for example, one-dimensional position x. Correspondingly, in quantum mechanics, we have a position operator x hat. We put a hat sign just like a unit vector on x and we call it x hat, just like if I have operator A, so I will have a hat or a cap. This represents operator. So for each dynamical variable in classical mechanics, there corresponds a quantum mechanical operator. For example, we have a position in classical mechanics. In quantum mechanics, we will have a position operator. In classical mechanics, we have a linear momentum. In quantum mechanics, we have a linear momentum operator. In classical mechanics, we have an angular momentum. And in quantum mechanics, we have quantum angular momentum operator. Likewise, energy. In classical mechanics, we have a total energy, mechanical energy, which is the sum of kinetic energy and potential energy. But in quantum mechanics, we have a Hamiltonian, which is the sum of kinetic energy operator and momentum and potential energy operator. So that is the addition of kinetic energy and potential energy operator is equal to total energy or Hamiltonian. Okay, all right. If I start its mathematical definition, an operator is a mathematical rule which, when applied on a cat, transforms it into another cat. And likewise, when it is applied on a bra, it transforms the bra into another bra. Okay, it's a mathematical, you can say, operator. Just for example, the differentiation, differential, integral, these are operators which, when applied on a function, transforms it into another function. For example, we have a differential operator d by dx. If I apply it on a function, let's suppose x square, then if I apply d by dx on x square, the answer will be 2x. So who changed the function, this differential operator? So operator means something which changes a function into another function. That is simple, a mathematical definition. I'm not going to dig out its physical significance. I'm just telling you about its mathematical perspective first. Then at the end of the lecture, I will discuss about its physical significance. So once I repeat, an operator A is a mathematical rule, mathematical, you can say, entity that when applied to a cat, let's suppose this is a cat, transforms it into another cat, psi prime, of the same space. And one thing is very important, that the space must be the same. If it's applied in a one, you can say the Hilbert space, the after the transformation due to the operator, the answer will be in the same space. For example, A operator in this equation, A operator applies on a cat psi, and it will transform it into another cat psi prime. But the left hand side of the equation and right hand side of the equation belongs to the same space, same Hilbert space. किसी और space में ये नहीं जाएंगे, it will remain in the same space. And likewise, if I operate an operator on a bra, let's say phi, it will transform the bra into another bra, let's say phi prime. Okay, so the basic functionality of the operator is to transform one cat into another cat, one bra into another bra. That's the simple. And if I don't rely on the Dirac notations, I simply write the operator's definition in the continuous basis, psi function of R. A applies on psi function of R, answers is equal to psi prime function of R. Psi prime is another wave function. So what A did, A transformed psi into psi prime. Similarly, if I operate A operator on phi, so then it will transform it into psi prime. Let's suppose if psi आप कह सकते हैं कि ये एक complex conjugate है psi का, then is a bra, and if A operate on a bra, it will transform it to another bra. So once again I repeat, if you have a cat, it will be transformed to another cat by the application of operator. If you have a bra, it will convert into another bra by the application of operator. There are some examples just to elaborate the idea about the operators. For example, you have a unity operator. Unity operator is that operator which leaves the cat unchanged, which leaves the bra unchanged. So the operator which leaves the function unchanged is called a unity operator. Just like one, if we multiply something by one, it will remain the same. So unity operator is just like that. For example, I apply unity operator I on a psi cat, it will remain the same. So this is called unity operator. There is a gradient operator, just like a differential. So gradient psi over psi x plus into I unit vector, psi partial over partial y into j unit vector plus partial over partial z into k unit vector. If apply on a function psi of r, then this will be partial over partial x into psi, partial over partial y into psi, partial over partial z into psi. And this is called a differential operator or gradient operator. So it will definitely calculate the slope of the function, slope of the wave function. Okay, let's move forward. Another example is the momentum, linear momentum operator. Linear momentum, you know, the momentum is equal to, in one dimension, it's equal to minus iota h cut partial over partial x. This is the value of momentum operator in one dimension. And we'll not go to its derivation at this point, but we consider it like as it is like this, that x component of the momentum operator px is equal to minus iota h cut partial by partial x. This comes from the actually from the uncertainty principle. We can derive it from the uncertainty principle, but I'm not going to its derivation. I'm just telling you the value. So in 3 dimension, momentum operator is equal to minus iota h cut into del. This delta operator multiplied by minus iota h cut, this is equal to the momentum operator. So p psi is equal to minus iota h cut del into psi. So this is the equation for the momentum operator. And likewise, Laplacian operator, you know, del dot del is equal to del square, which is the Laplacian. And this is equal to partial square by partial x square plus partial square by partial y square plus partial square by partial z square. It's a scalar operator, you know, from the electrodynamics. So this is the Laplacian operator. When applied on psi, it will definitely transform psi into the second derivative, which is equal to curvature of the function. First derivative is equal to slope of the function. Second derivative is equal to curvature of the function. So this is also an operator. Another example is parity operator. Parity operator is actually just gives the mirror image of the function. If you have at the point plus r in a function, its mirror image will be equal to at minus r. So that is the called parity operator. If I apply parity operator on a wave function psi, it will move it to the equal to psi at minus r. This is at plus r, this is at minus r. So at plus r and minus r are the mirror images. These are called parity operators. If you are at plus r position, parity operator will move you symmetrically on the minus r position. So that is an example of parity operator. So what we concluded from here, that actually this operator changes one ket into another ket, just like this psi of r is one ket, one wave function on state, and this parity operator changes it psi equal to minus r, another wave function. So operator simple is that rule, that mathematical rule, which changes one state of the system into another state, one ket of the system into another state, another ket, one bra of the system into another bra. Likewise. So this is a basic definition of the operator. So in classical mechanics, we have dynamical variables, position, momentum, angular momentum, kinetic energy, potential energy, total energy. These are the famous list of dynamical variables in classical mechanics. In quantum mechanics, we have the same familiar list of the operators, quantum mechanical operators, position operator, momentum, linear momentum operator, angular momentum operator, kinetic energy operator, potential energy operator, and total energy operator, which is also called Hamiltonian. Hamiltonian is equal to kinetic energy operator plus potential energy operators. Operators have the same role in quantum mechanics what dynamical variables have in classical mechanics. In classical mechanics, once we have the position of the system, then we can calculate other variables like velocity, like linear momentum, and everything else, if we have the boundary conditions and the initial position of the system. And in quantum mechanics, if we have the wave function of the system, we have calculated wave function definitely from the Schrodinger equation, then we can also apply different operators to get the eigenvalues of the operators values from that wave function. For example, if we apply a momentum operator, we will get momentum eigenvalue, which will be useful for the information of the momentum of the particle. Okay, now I'm going to start some of the properties of the quantum mechanical operators. Rather, it's very general, not we are going to specify momentum or position or angular momentum operators. We are just considering two general operators, A and B operators. Just for the sake of generality, we are doing this, and at some point we will go very specifically to the position and momentum operators, position and angular momentum operators, and so on. But at the starting point, we are just generalizing the ideas. For example, we have A and B operators. Then product of A and B is not generally equal to product of B and A. Means A and B, two operators, are not generally commutative. Means if we change their order, the answer will be changed. Like this, AB is not equal to BA. It means if we apply B operator on a function psi first, and then we operate A operator, the result will be different if we apply operator A first and secondly operator B. Okay, if we first apply B and then A, the result will be different. If we apply first A and then B, the result will be different. It means the sequence of application of operators matters. Sequence of operators is very, very important. If you have a different operators like A, B, C, D, E, and you change the order of operation, means first you operate E, then you operate D, then B, C, then B, then A. This is one sequence. If you operate A first, then B, then C, then D, then E, the result will be totally different because operators are not commutative. The order of the sequence of the operation of these operators matters. And this is very, very important in general. But in some cases, the order doesn't matter. In some cases, we will discuss in next lectures that in some cases the order doesn't matter. If you operate B first and then A and change the order, the results will be same. Those operators will we will call that those operators are commuting each other. And in generally, AB is not equal to BA. It means the operators are not commutative in general. Okay. Then if you are operating two operators at the same time, A and B are two operators, and we are operating on a state psi, what it means? It means we are operating B first, and there will be an answer, and at that answer we will operate A. It will be like this. This bracket shows that B operates first because the most closest operator operates the first. B is the most closest to this cat. And always it's a rule, you can take it as a rule of thumb, that the operator which is with the straight line of this cat always operates it. It operates on the cat from this straight line, not from this greater than sign. So B operates on psi first, as it's shown in bracket, and then on this answer of this one, answer of this one, A operates. It's something like this. Okay, then we define linear operators. What are the linear operators? Linear operators are those operators which have the distributive property. Distributive property is what that if let's say we have not a single state, but there are two states, psi 1 and psi 2, and there is a linear combination, means sum of the two states with the multiplication of some scalar values. A1 and A2 are the scalar values. So sometimes we have a cat psi, and sometimes we have a linear combination of the wave function. And if let's suppose we have a linear combination of the wave function and operate a vector A, it will operate on the first term, it will operate on the second term, just like a simple multiplication. This is called the distributive property, means the operator distributes itself. So this A operates on this psi 1. So A1 which is a scalar will go outside, and this operator A will operate on this cat. And likewise, this operator A operates on A2. This type of operation in which the operator distributes itself into all the terms, these operators are called linear operators. The operators which obeys the distributive law, which distributes themselves on each term of the wave function, a linear combination of the wave function. Such type of operators are called linear operators. And similarly, like bras, these are the bras, psi1 bra, psi2 bra, and I operate A. Now, consider this point what I have told you before, that this operator A is now on the right side. Why on right side? Because it have to operate on the straight line of this okay state, not from this less than or greater than sign. It have to operate on the straight line side. This is the side of operation, you can say. And this A has distributed itself with the E term, this one and this one. So this is called the linear operators. Okay, I stop here. Next time I will tell you about the Hermitian operators, Hermitian adjoint, and then properties of the Hermitian and skew Hermitian operators. This is very important. And then I will tell you about the projection operators. So this will complete this topic of operators. Now I stop at the middle. I'm not going to tell you about the whole thing about the operators. Tomorrow I will discuss about the Hermitian operator and projection operator, and at the end we will discuss some of the physical significance of these operators as well. And if you have the questions, you may write the questions in the uh, chat box as well, and you can also send me the audio messages on the WhatsApp group for the questions. So please write your questions in the chat box. I will also, some of the students have comments that audio is audio is not clear. So I will put this lecture on the YouTube as well, so that you may again listen the lecture. And if you have the questions, please write it in the chat box, or you can also send me audio message in the WhatsApp group. Thank you very much.